Welcome all of you. So, we are now currently discussing shear strength of soils. In the last lecture, we have seen shear strength of cohesive soils, and we have noticed that there are 2-3 important aspects which we should be knowing very well to understand the shear strength behavior of cohesive soils properly. One is the drainage condition, which results in drained and undrained conditions, and the other aspect is with respect to stress history. Now, with respect to drainage condition, let us say when we have a undrained condition existing, the net result is the pore water pressure. And as we have already seen in the past, and when we have understood soil mechanics for the first time, we know that voids, the pore water present in it and the pore water pressure makes soil mechanics different from the other solid mechanics. So, in today's lecture, we will discuss a bit on pore water pressure. Now, in advanced soil mechanics, why we should bring this subject again? So, in undergraduate we have learned about pore water pressure and the method of calculating effective stresses, but in this we will try to understand a bit more in detail, like if we need to predict pore water pressure, normally it is measured. Now, in certain circumstances, for solving some problems numerically, you also need to have what is the undrained condition, what sort of total stress that gets developed, and what is the kind of effective stress which is responsible for the soil mechanical behavior. If that is the case, we also need to have the knowledge of pore water pressure. So, we will get into some details of pore water pressure, the method of prediction of pore water pressure, and certain other aspects which are very relevant for module 3 and module 4. Again, we are building up the platforms. In all these subsequent lectures, what we are doing is we are building platforms for a better understanding of module 3 and module 4. So, let us start with pore water pressure. So, importance of pore water pressure. So, when total stress, now total stress we say it is the external load which is acting, this also we have seen. When we say total stress, that is the stress acting on the medium. When total stress is applied on a saturated soil mass, there is an instant increase in pore water pressure, nothing new. The rate at which total stress is applied and the rate at which pore water pressure dissipate are critical factors that governs the mechanical behavior of cohesive soil. So, whenever we say mechanical behavior, we know that it is effective stress condition which is important, but undrained condition do exist. Now, the rate of loading governs what type of undrained condition it has and how much of the pore water pressure gets developed. Now, the hydraulic conductivity of the soil determines how fast the pore water pressure dissipates. Now, these two jointly determines what will be the effective stress which is gained in the soil at a given time and what will be the equilibrium effective stress and when it is going to reach, because all these factors it influences the mechanical behavior or the stress strain behavior or the strength of the soil. Let us see a typical construction sequence. Now, for comparison, I have placed the drained response as well, where the soil drains fast and there is no possibility of development of pore water pressure. So, the first figure represents how total stress changes. That means, let us say there is a construction that is happening, there is a foundation and there is a building load which gets added up, or maybe an embankment load which gets added up. Now, what happens? The total stress increases with time. So, this is the pattern in which the total stress increases. Now, what is the instant response when a soil mass, a saturated soil is loaded? There will be pore water pressure. Now, since this is a completely drained response, you can see that there is no development of pore water pressure. So, it is at 0. So, this can be treated as 0. Now, it remains same. Now, what will be the change in effective stress? Since this is 0, whatever is the total stress, that will be the gain in effective stress, as you can see here. So, delta sigma dash is equal to delta sigma. This is at equilibrium, but any point along the curve also this is satisfied, because it is a drained response. Similarly, there is a volume change has happened, and this is a typical compression case where it compresses and it follows the same sequence as that of the loading. Now, let us see the undrained response. Let us say that this is the increment of total stress, this is the loading, and after this particular point it remains constant. So, let us see what happens for pore water pressure. In the case of pore water pressure, this is the instant response. Now, this is an undrained response where water is not allowed to drain off fast. So, there will be a mounting of pore water pressure. Since it is saturated, there is an instant capture of delta sigma in terms of delta U. So, whatever is the change in total stress, that remains same in the case of pore water pressure up to this particular point T. Now, for us as a layman, there is no further change in total stress, that is, there is no further change in loading. So, as a layman, one would always understand, okay, we have already completed the loading on the soil mass. Till now, nothing has happened to the system. So, there is nothing to worry. Now, this aspect gets defeated when you know or when you learn soil mechanics. The reason is, whatever has to happen will happen after the completion of construction or after the external load gets completed. So, that is what you can see here. Now, after the construction got completed, beyond that point, the pore water pressure will slowly get dissipated, and the excess pore water pressure it tried to achieve, or it becomes close to 0. I am cautiously using the term close to 0 because there will be some differences. So, whatever be beyond the construction period, the pore water pressure starts reducing. Now, what is the net effect? You can see that the effective stress remains 0 till the construction got over, because that is a saturated system, and whatever loading, it is all captured by pore water pressure. And beyond the construction stage, you can see that the effective stress which starts increasing. Now, effective stress starts increasing, you can see that beyond a certain time period, whatever is the total stress applied, what is the load applied, effective stress becomes equal to that. So, change in effective stress is equal to change in total stress after some time. Now, what is the net effect of this? As the intergranular stress goes on increasing, as the effective stress goes on increasing, this will induce some sort of volume change. So, that volume change you can see till the construction got over, there is no volume change which is happening. Now, all the volume change happens after that. Now, this particular information is very vital to understand what is the importance of pore water pressure. So, at the end of the construction, it is important for us to assess what will be the kind of pore water pressure. Either it is measured or it is estimated. Now, it is not possible to measure always, because instrumentation for us is pretty costly. Only in very, very important projects, instrumentations are done and it is monitored. But in normal cases, to understand the effect of pore water pressure, it is not always possible to measure it. Rather, it is estimated, and that is the whole crux of today's lecture, that we will try to see how we can estimate pore water pressure. This is what I am summing up. There is no increase in external loading. U excess, that is excess pore water pressure, start dissipating. There is an increase in effective stress which results in volume change. Now, volume change is nothing but settlement. as a function of time. Imagine in the case of an embankment or a building, the settlement happens once the construction phase gets over. So, if we do not anticipate the kind of pore water pressure, if we do not estimate the kind of pore water pressure that we anticipate in the field, which is dependent on the soil characteristics, then we may end up in trouble. That is why there are lots of failures that has happened in terms of settlement. So, with that topic very clear that pore water pressure need to be estimated, let us see how we can go for prediction of pore water pressure. So, it is apparent that the knowledge of pore water pressure is mandatory for undrained loading. Change in pore water pressure delta U with change in total stress is necessary for different projects like water retaining structures, where it is bound to be undrained and pore water pressure keeps changing. Prediction of pore water pressure with different loading conditions are necessary for what? To define the effective stress, and then effective stress dictates what is the mechanical behavior of soils. Loading conditions are in terms of total stress change, that we have to keep in mind whenever we say loading on a soil, that is always expressed in terms of total stress. Now, total stress change can be in terms of hydrostatic, which causes volume change, and deviatoric, which causes shear failure. Both are important. Pore pressure develops for each of the loading stages. The concept of pore pressure parameters were introduced for predicting excess pore water pressure under different loading conditions. So, the bottom line is we will be introducing something known as pore pressure parameters for predicting the excess pore water pressure corresponding to whatever is the loading condition. Now, those who have understood this concept of pore water pressure parameters, still I would suggest that you go through this in detail, because this chapter and this discussion is important in stress parts as well. So, having known that pore water pressure parameters are important, let us see Skempton's pore pressure parameters defined A and B. And this is an age old paper in 1954. It is published by Skempton, the pore pressure coefficients A and B in geotechnique in 1954. But over all these periods, I think this still remains a fundamental aspect in many of the soil mechanics problem. So, it is important for us to know what was the genesis or where it all started with. So, Skempton's pore pressure parameters A and P becomes very important. There are different variants of this, but the concept remains the same. An increase in principal stresses, which is defined in terms of, that is total stress and external load whatever be, that is defined in terms of principal stresses. So, any increase in principal stresses results in delta U under undrained condition. Dissipation of delta U causes volume change, we have known this. Now, for deriving this A and B, we need to do some indirect approach. Let us see what it is. Let V, capital V, be the initial volume of soil skeleton. When we say it undergoes volume change or there is pore water pressure, it is all associated with some sort of strain. We know the elastic volumetric strain epsilon V, which is defined as minus delta V by V, that is change in volume upon original volume, equal to 1 minus 2 mu by E delta sigma 1 dash plus sigma 2 dash plus sigma 3 dash. Note, this is a drained condition characteristics where effective stress characteristics are used. So, volumetric strain is always associated with drained condition. Okay. So, that is why epsilon V is minus delta V by V. So, this is the expression, and this we have seen already in the previous lecture. Now, this we know is a drained condition response. Consider undrained condition with no drainage. Now, this is what we actually need. Assume some sort of volume change occur under fully undrained condition. Now, this is not a possible condition. this is not a possible condition, because under undrained condition only pore water pressure develops, but we are adopting an indirect method for obtaining this pore water pressure. So, what we are doing is we are trying to assume, make an assumption that there is some volume change that has happened in an undrained condition. Now, what could be the possibility of such a volume change? Now, this is possible only if volume change occur due to the compressibility of water, which is associated with delta U. Now, there is delta U, water, let us assume that water is compressible, and because of this compressibility property, the volume change can happen during undrained condition. Now, water is incompressible, it does not undergo volume change, so that concept remains same and it is very well valid. But here we want to understand, we want to determine what is delta U. So, that is why we are making such an assumption. So, we associate that assumed volume change in undrained condition to compressibility of water. So, mathematically, change in volume under undrained condition due to delta U, which is associated with compressibility of water, can be expressed as minus delta V is equal to VW CW delta U. Minus delta V is the whatever volume change that has occurred under undrained condition, which is associated with compressibility of water. Now, compressibility of water is CW, and VW is the volume of water in the voids. Since it is saturated, volume of voids remains equal to volume of water. Delta U is the pressure which creates this volume change. Now, you may be wondering from where this expression has come. This is similar to consolidation settlement equation. You might be remembering this equation very well. This is consolidation settlement SC, which is equal to H mv into delta sigma dash. Delta sigma dash is the one which causes this settlement. What is settlement? It is nothing but the volume change. Here it is one dimensional, so it is delta H. Instead of delta H, here it is delta V. So, that SC corresponds to delta V here. H is the original height. Here it is what is the original volume, and here we are associating the volume change to only the compressibility of water. So, where is water? Water is in voids. So, volume of water which is equal to volume of voids becomes the original volume. So, H corresponds to volume of water here. MV, MV is coefficient of volume compressibility in consolidation. The same property which represents compressibility of the soil skeleton, here it is CW, which is exclusively related to compressibility of water. And what causes this settlement, that is delta sigma dash in consolidation, here the volume change is caused by delta U. Please remember, this is assumption. Now, we can also write VW, we can replace VW by total volume. How? Because N is porosity. N is the porosity, Cw is the compressibility of water, and N porosity is equal to volume of voids upon total volume, which is equal to volume of water upon total volume. So, you can always write N into V, that is Vw is equal to N into V. So, that is what has been replaced here. So, we can write minus delta V by V is equal to N Cw into delta U. Now, this is already obtained in the previous slide. So, if we equate these two, N Cw delta U is the volume change that has occurred, we are now trying to equate these two. In essence, like, it does not make much sense because this is not going to happen, but then we are assuming that it is going to happen, and that volume change is associated with the volume change that would have happened under drained condition. So, delta U is the term what we need. We need to estimate what is the excess pore water pressure that gets generated. So, delta U is equal to 1 minus 2 mu by E, N and Cw comes down. So, N E Cw, this remains same. Now, triaxial condition is a very prominent condition in the lab. So, let's now specifically discuss about triaxial condition. What is triaxial condition? We have delta sigma 2 dash is equal to delta sigma 3 dash. So, if you put that, we have delta sigma 1 dash plus 2 delta sigma 3 dash. Delta u is equal to 1 minus 2 mu n E C W. We can replace the effective stresses by total stresses. So, delta sigma 1 minus delta u plus 2 into delta sigma 3 minus delta u. So, this we can write 1 minus 2 mu, this remains same, delta sigma 1 plus 2 delta sigma 3 minus 3 into delta u. So, you have delta u here and here. So, I can take this 3 delta u on the other side, and when you take it to the other side, do not forget about this particular expression. It will be 1 minus 2 mu by n E C W 3 delta u will go on the other side. So, this will become plus. So, that is what is written here, 1 that comes from this delta u plus whatever has come from right hand side to left hand side plus 3 into 1 minus 2 mu n E C W delta u is equal to whatever is remaining here. So, delta 1 here what we have done is we have done another some arrangement, mathematical rearrangement. Delta sigma 1 plus 2 delta sigma 3, we have just made some modification. You are adding and subtracting minus delta sigma 3 and plus delta sigma 3. So, this gets added, becomes 3 delta sigma 3, what is written here, and delta sigma 1 minus delta sigma 3 is given here. You do the mathematical modification again, that is n E C W plus 3 into 1 minus 2 mu, this gets cancelled off, into delta u is 1 minus 2 mu delta sigma 1 minus delta sigma 3 plus 3 delta sigma 3. So, delta u will be equal to 3 into 1 minus, I am taking this 3 outside. So, 3 into 1 minus 2 mu upon this part comes down n E C W plus 3 into 1 minus 2 mu is into delta sigma 3 plus, so 3 goes outside. So, delta sigma 3, so there will be 1 by 3 of delta sigma 1 minus delta sigma 3. So, finally, we get the expression delta u is equal to 1 by 1 plus n E C W upon 3 into 1 minus 2 mu into this term remains the same. So, I can replace, we will take this E downwards. So, it will become 1 by 1 plus n C W upon 3 into 1 minus 2 mu by E. So, that is replaced by C S. This again remains same. Now, C S is known as compressibility of soil skeleton, which is equal to 3 into 1 minus 2 mu by E. So, the expression for delta u is with an assumption that the saturated soil, first of all it is for saturated soil, it behaves as perfectly elastic material, and this expression corresponds to that. This expression whatever we have obtained, it corresponds to first of all saturated soil, this corresponds to saturated soil, it corresponds to triaxial condition, and it also goes by the assumption of perfectly elastic. So, these are some of the conditions which are pertaining to this particular expression. So, delta u is due to change in confining pressure, because delta sigma 3 is related to confining pressure in triaxial testing, and change in deviator stress delta sigma 1 minus delta sigma 3. So, there are two components, one due to confinement, the other due to the deviatoric component, both results in delta u. So, the equation for delta u can be written as delta u is equal to B into, that is the whole of this is denoted as B into delta sigma 3 plus A into delta sigma 1 minus delta sigma 3. Now, 1 by 3 is replaced by A, that is 1 by 3 replaced by A. Why? Because 1 by 3 corresponds to strictly a perfectly elastic condition. Now, we will not expect soil to behave as elastic like any other material. So, for generality, so to deviate from elastic behavior, to give that option, we have introduced, Skempton introduced A parameter. So, this equation was proposed by Skempton in 1954. So, A and B are very popularly known as Skempton's pore water pressure parameters. The use of A and B becomes prominent in the subsequent chapters. So, it is important to understand this. So, now the same equation, this equation is written here, and if you take B inside, it is B into delta sigma 3 plus AB into delta sigma 1 minus delta sigma 3. So, B into delta sigma 3 plus A bar into delta sigma 1 minus delta sigma 3. This is an alternate way of representing this pore water pressure, where overall pore pressure parameter A is defined. Now, it is a simple rearrangement of the equation. Now, we will discuss a bit about both these parameters, what are its physical significance. The first one is pore water pressure parameter B, which is given as 1 by 1 plus NCW by CS. Now, let us say the situation is for completely saturated case. If it is completely saturated, now we have assumed water to be compressible, but in fact water is not compressible. So, Cw for a completely saturated state when there is only water, Cw tends to 0, even though we made an assumption that it is not. So, that whole assumption was to correlate for obtaining delta U. So, if there is no volume change which is going to happen, then what is going to happen? So, that was the kind of logic which was used. So, when for fully saturated case Cw approaches 0 and hence B value will be equal to 1. So, this clearly indicates for a fully saturated system B is equal to 1. Now, what is happening to partially saturated soil? So, the same expression, instead of Cw it becomes Cf, where Cf is called compressibility of pore fluid, which includes both water and air. Now, it becomes more compressible, it is not equal to 0 because the contribution of air is there, which is highly compressible. So, 1 by 1 plus NCF by Cs. Now, what is happening? This component is no more 0, it is an appreciable amount. So, in partially saturated, this is what it is, UA, the pressure is more, UW, which is held in the pores, the pressure is negative, that is U is 0 and UW is negative, that we call it as negative pore water pressure or soil suction, and UA is greater than UW. The compressibility of the whole system is now more than 1 and it is appreciable. So, Cf is very much greater than 0 due to high compressibility of air. Now, what is the net result because of this? For example, it is a dry state, completely dry state, Cf is only due to the contribution of air, this will be exceptionally high quantity. Now, if this is very high, the whole of the B comes down drastically and it will be very much close to 0. So, that is what is written here. For dry state, B value is 0 because Cf, this denominator becomes very high. Now, as saturation increases from dry state, as the saturation increases, the B value also increases. By the time it reaches fully saturated, B is equal to 1. So, the range of value of B is in between 0 and 1, where 0 indicates dry state, 1 indicates saturated state. B parameter hence can be used to represent soil saturation. So, this parameter B is a very good indication of saturation. Now, as the confining stress increases, air expels or it gets dissolved in water, saturation increases and B value increases. So, this is a very effective way of using B parameter for ensuring the saturation of triaxial soil sample. We all know and we have seen in triaxial testing, the first procedure is after mounting the soil is to get it saturated, because conventional triaxial testing we discuss only about saturated soil. So, you need to saturate the soil first and we need to know whether it has actually got saturated. Now, B parameter, which comes from Skempton's pore pressure parameter, is used to check whether the soil is saturated or not. This will become clear in the subsequent slide. Now, let us talk about pore water pressure parameter A. We have already seen A is equal to 1 by 3 for perfectly elastic case and triaxial loading. Please note, this is also important. Whatever we have discussed as Skempton's equation is with respect to triaxial loading. But we know soil is not perfectly elastic, so 1 by 3 is not valid always. So, that is why it is replaced by A. A parameter changes with loading or with increase in deviator stress. That means there is a variation of A with loading which takes place. So, there will be initial A. So, before the starting and during the loading A changes, and finally there will be at the failure condition there will be a value of A which is denoted as AF. So, AF is the A parameter at failure. Now, the value of A is also influenced by stress history depending upon whether it is OC or NC. Normally AF varies between minus 0.5 and 1.5, that is what has been observed in the lab. So, this is typical AF values which is given by Skempton in his paper 1954, where we can see that, for example, normally consolidated clay, it varies from 0.5 to 1, and for a heavily over consolidated clay it is from minus 0.5 to close to 0. This clearly indicates that the stress history of the soil influences the parameter A, and with loading also the A will change, because it is A is associated with deviator stress and deviator stress keeps changing. So, the A value also changes. So, now delta U for different stages of loading in a triaxial compression testing. So, we have discussed about triaxial condition here. So, let us see how delta U develops for different stages of loading. So, the first stage is confining stage. Soon after saturation of the soil sample in triaxial testing, we go for confinement, application of confining stress. Now, if it is an undrained condition, how pore water pressure develops, that is what we will see now. So, this is a typical triaxial sample, and delta sigma r is the confining stress, where delta sigma r is equal to delta sigma 1 is equal to delta sigma 3. It is an all round stress condition, only volume change happens. Now, if it is an undrained condition, volume change will not happen, but pore water pressure increases. The excess pore water pressure for confining stage is represented by delta UC. So, substituting this in the equation of Skempton's equation, we can write delta UC is equal to B into delta sigma 3 is very much there, that is the all round pressure, plus A into delta sigma 1 minus delta sigma 3. Now, this is equal, so it becomes 0. So, B is now equal to delta UC by delta sigma 3. Now, this is where I told it can be used to check whether the triaxial sample is saturated or not. When will it be saturated? When B value is equal to 1. So, if you have done saturation, if you have done the triaxial testing in the lab, you would have definitely looked for B value. Now, how B value represents 1? Now, if for a fully saturated condition, what happens is, whatever is the increase in delta sigma 3, that will be fully reflected by delta UC. If there is some amount of air present in the sample, whatever is the load that is applied, that is delta sigma 3, what is the total stress which is applied delta sigma 3, it will be partitioned between pore water pressure delta UC and some volume change that happens because of the expulsion of air. So, it is not 1:1. Hence, delta UC will be always less than delta sigma 3. So, B value will be less than 1. and that is how it is. So, if you improve the saturation and the whole of the pores are filled with water, whatever delta sigma 3 is applied, that will be reflected as delta U. But it is very hard to get the value 1, but it will be close to 1. Anything above 0.9, 0.95 can still be considered a saturated sample. So, after completing the confining stage, then we go for the deviator stress, that is the loading stage. Now, here please be careful, this is the soil mass to which delta sigma 3 was already applied. So, the all round stress is there. Now, you start increasing the axial load, which is delta sigma 1. Now, here in the loading stage, delta sigma 3 remains constant, or sigma 3 whatever has been applied in the beginning is not changing in the loading stage. So, delta sigma 3 there is no change in the all round stress. So, this becomes 0. So, whatever axial load you are applying, that itself will be delta sigma d or delta sigma 1, but the concept of delta sigma d is what causes failure in the triaxial soil sample. Now, what stress causes failure? Whatever axial load that has been applied, delta sigma 3 was already existing before. So, whatever is causing failure is the total load minus whatever has been applied onto the sample minus this whatever was there initially, that is delta sigma 3. So, that is how it becomes delta sigma 1 minus delta sigma 3. This sigma d is very much valid for the failure condition, but here in this case we should know that whatever is the axial stress that we are applying, that is delta sigma 1, and that remains delta sigma 1 because there is no increment in delta sigma 3. So, delta sigma 3 is equal to 0, and hence delta ud is equal to B, that is the pore water pressure corresponding to loading stage or deviated stress stage is B into delta sigma 3 is 0 plus A into delta sigma 1, delta sigma 3 is 0. So, that here in this case it is saturated, so B is equal to 1. So, you can write AF, that is the A parameter at failure is equal to delta UDF by delta sigma 1 F. So, this both corresponds to at failure condition. What is the delta sigma 1 at failure and what is the pore water pressure at failure. So, AF is defined. So, the final stage is the summation of these two, which is delta UF. So, you have delta sigma 1 and delta sigma 3 acting, and total pore water pressure at the end of the stage is equal to the one which comes from the confining stage and the one which comes from the loading stage. So, the parameters A and B are determined in the lab for the condition simulated close to field problem. So, if you want to apply this for estimating the pore water pressure corresponding to any given geotechnical problem, we need to understand what is the A and B parameter. B is not important, A is important. What is the kind of A parameter corresponding to that soil for that particular field condition. So, this is a typical variation of A parameter for with respect to stress history. This we have already discussed what will be the kind of stress strain response. This is a strain hardening and this is strain softening for NC and OC. For corresponding to NC, for an undrained condition, the pore water pressure will be positive. So, this is positive. Whereas for OC, there will be initial compression for OC in the volume change, that corresponds to a positive pore water pressure in the beginning, and then it comes to negative. For OC, because OC tends to dilate. So, those which tends to dilate will try to suck the pore water inside. So, that is negative pore water pressure. So, that is given here. So, pore water pressure will be negative for OC or it keeps on reducing. So, correspondingly the A parameter for NC, you can see that it will reach close to 1 at the end of the test for NC, and for OC it will become progressively negative. So, you can see this close to minus 0.5 for OC. So, to summarize this chapter, it is pore water pressure prediction is important for studying the undrained behavior of cohesive soil. Skempton's equation with parameters A and B can be used to predict the pore water pressure as a function of change in total stresses. This pore water pressure equation corresponds to triaxial condition that we have already seen, and it is estimated in two stages, one corresponding to confining stage, the other one is loading stage. Pore pressure parameter B represents soil saturation. For fully saturated, B is equal to 1, completely dry, B is equal to 0. So, B parameter helps to assess saturation of triaxial soil sample. Parameter A changes with loading, and A value at failure is considered as AF. A parameter is influenced by stress history of soil. For triaxial loading and considering soil to be perfectly elastic, the value of A is equal to 1 by 3. So, that is all about pore water pressure estimation using Skempton's equation. In the next lecture, we will see that how to use this, the same equation rearranged in a different format, and how that becomes important for certain field problems. That is all for now. Thank you.